In this lecture, we will see the pin diagram of the 8085. So, it is a, as mentioned in the previous slide, it has got a 40 pins. So, it has got 40 pins. So, it starts from pin 1 and then goes to 40. So, what are the various pins? So, we will see later units, we will see in more detail about the function of various pins. At present, we will see some important pins. So, the microprocessor has to address the data and take the data in and then out. So, it requires pins to address the memory location. Since it has to it is capable of addressing 64 kilobytes of memory. So, it requires a 16-bit binary number. So, 16 pins are required to send the 16-bit binary number to the memory, so that it can go from location 0 to location 64,000. So, 16 pins. So, these are the pins, these are the address pins. So, A0 to A15. Okay. So, it starts from A0 and then goes to A15. But then it has to it deals with 8-bit data. So, it requires 8 pins for receiving and sending the data. Okay. So, it requires 8 data pins also, but 16 pins for address and 8 pins for data. Then the number of pins in the microprocessor will increase, then it requires the other pins also, then the number of pins in the microprocessor will increase beyond 40, then the size will become large. Therefore, what it has been done is, so part of these pins are shared by address and then the memory. So, you can see here, and here also it is written as multiplexed address and data bus. Multiplexing means, so same pin is used for two purposes. Okay. So, this pin, these 8 pins are used as address as well as data. A means address and as well as data. Data consists of 8 bits starting from bit D0 to D7, and then address consists of again 16 bits starting from A0 to and then A15. Okay. So, this is exclusively for address. So, these higher order pins, they are exclusively for address, and then these pins are address as well as for data. So, you have to have some signal to distinguish whether whatever you are getting from here are address or data. So, the signal that is coming from here or the bits that are coming from here may represent address or data. So, how to distinguish it? So, you have what is called as the address latch enabled signal. So, this address latch enabled signal will distinguish whether you are getting data or the address. So, how it does, of course, we will see in the other slides. Okay. So, as I already mentioned, the 8-bit general purpose processor, and it can address 64 kilobytes of memory, and it has got 5 volts, it works at 5 volts power supply, and frequency of operation is 3 megahertz, and of course, it can go to 6 megahertz also. And so, it has 40 pins. Okay. So, 40 pins, they are actually grouped as address pins and then data pins, and then you have to control the read operation, write operation, and so on. So, for that control pins, and then the power supply pins. So, it requires power supply and ground, and you have everything, every operation. So, the microprocessor requires clock pulses. So, you have the pins to generate the clock pulses, and microprocessor should respond to some external signals. Okay. Some important information, some important events, the microprocessor should immediately respond. So, for that some important external events, the microprocessor should respond. So, you have some pins devoted, so that whatever anything happens, any change in the pin, that is either 0, 1, 1 to 0, like that, some changes in the pin happens. So, the microprocessor will respond. So, they are called as externally initiated signals, and then so the microprocessor is allocated few pins for that. And then another thing is serial communication. Okay, serial. So, although it is a 8-bit processor, so if you send the 8-bit data simultaneously, okay, you require 8 lines. Okay. So, if you send the data from say from your processor to the printer, so simultaneously if you send all the 8 bits, so you require 8 line, your cable should have 8 wires. Okay. So, that will make the cable expensive, and so you can send the data one after the other. so in a serial form. So the microprocessor has also got serial ports. Okay. So now we have shown the entire pin diagram in terms of group. So previous pin what we have shown is they are as per the data sheet, as per the microprocessor data sheet. So the pins given by the manufacturer as it appears physically, we have shown. Now for our understanding purpose, we have grouped the pins and we are showing here. So the microprocessor has got address pins. Okay. So this is the higher order address, and then you require 16 address pins. Okay. So in the 16 address pins, so the 8 pins of the microprocessor, they are shared by data also. Okay. So these address pins, so they are represent the higher order address. Okay. So they are unidirectional, they send only the address. Okay. So the address is being sent by the microprocessor, that means they are unidirectional. Okay. So this will identify the memory location as well as the other peripheral location of the peripherals, and then these pins are shared by address as well as the data. That means data means you should send the data as well as receive the data. So that means it is bidirectional. For when it works as a address, it sends in this direction. When it works for data, it may send as well as it will receive. So it is the bidirectional bus. And then you have to initiate the read operation, write operation, and then you have to distinguish between memory location and then input output port location. For that you have the control pins. Okay. So these control pins, what you see here, so they will synchronize the various operation with reference to clock, and they will time the read operation, write operation, data and other data transfer operations between the memory and then the I/O ports, and you have the serial I/O ports, because as I already mentioned, if you want to send 8-bit data simultaneously, you will require 8 wires, which may make your connection more expensive. So you should be able to use use a single wire or 2 wire, okay, and send 1 bit at a time. So for that we have serial input as well as serial output. Okay. Then the processor should respond to some external event also, some immediate events happening outside. Okay. Should be able to trigger the processor and take action. Okay. You should be able to trigger the processor at any time and deviate its programming path. So for that some pins are provided. Okay. So we will see all those things in detail in the other units. Okay. At present you please take note that they are called as externally initiated signals. Okay. So these are the 8085 pin configuration grouped in a convenient manner, so that you can very easily understand it. Okay. Now let us see about the architecture of the 8085 microprocessor. So this is the internal architecture of the 8085 microprocessor. So in the internal architecture, as far as we are concerned, we will be writing the program for the microprocessor in assembly language. Okay. So for program purpose, so it is enough we know few of the registers. Although so many things are shown, as a programmer it is enough we take note of only few of these registers. So although there are several things that are shown here, so whatever that is shown here in this light yellow color, they are the important registers which will appear in the program, in our program, and we can access these registers through our software. But other registers all are required for its working. We will not be able to mention that in our program, or we will not be able to access them using our instructions. Okay. So internally all the registers, so it's a 8-bit processor. So internally all the registers are connected by using this 8-bit bus. So to perform the arithmetic and logic instruction, we have the AL unit, and then to control the timing, read, write and other operations, we have the control unit, and then these are the registers. So these registers are general purpose registers. Okay. B, C, D, E, H, L, and then we have what is register to. So these registers hold data. So there are registers to hold the address also. So obviously the data registers are 8 bits. Okay. And then the address registers, since the microprocessor addresses up to 64 kilobytes of memory, so it has got 16 bits as address bits. So, they are all 16 bits registers. So, 2 address registers, 1 program counter and then stack pointers are there, and then all arithmetic logic operations are performed in this the results will be stored in the accumulator. So, one of the operand has to be, when you are performing an arithmetic operation, 2 operands, one of the operand has to be in the accumulator itself. So, depending upon the results of the what you get after an arithmetical logic operation, some registers, so some individual registers, okay, will be set. They are called as the flag registers. Okay. So, now let us see in more detail, okay, a simplified programming model of the 8085. So, this is a simplified programming model of the 8085. So, the 8085 contains an accumulator. Okay. Then to perform logic and arithmetic operation, we have the arithmetic logic unit, and after the logic and arithmetic operation you may get a result. The result may overflow. When you add 2 numbers, there may be overflow, and you may get 0 as the result, and so on like that. So, depending upon the result, so some individual flip flops. So, the flag contains again registers, okay, individual flip flops. So, these flip flops will be set or reset. So, they are called as the flag register. Okay. Then the instructions are given, of course, in the binary form, and that is the machine language. So, the instruction decoder will decode. Okay. So, you give the binary pattern for add. So, the function of this is to decode that pattern and then perform that particular task. Okay. Then you have the general purpose registers, which serve as a small memory. Okay. So, this is called as the register array, and then you have to send address. You have to address the memory location by sending the 16-bit binary word. Okay. So, that address is stored in 16-bit registers. So, we have program counter and then stack pointer. Okay. So, everything is controlled, timed and controlled by the timing and control unit. So, you have the address bus 16-bit and then data bus, that is 8-bit, and you have the read, write and other control signals. They are the control bus. They are called as the control bus. Now, we will go in more detail about the registers that are there. So, this is the diagram of what are the registers that are there in the 8085. So, the first register is the accumulator. Okay. So, this is denoted by the symbol A. So, it is a 8-bit register. So, all arithmetic and logic operations will take place only in the accumulator, and one of the operator. So, when you perform operation between 2 operands, one of the operator has to be in the accumulator. Then you have the general purpose registers. Okay. So, B, C, D, E, H, L. So, these registers can be used as 8 bits, or they can be used together as 16 bit also. That is, D and E can be combined and you can use it as a 16 bit register, and similarly H and L can be combined and you can use it as a again as a 16 bit register. Then you have to have registers to hold the address. Okay. One register, that is the program counter. Okay. So, the program counter contains the address of the memory location. So, the content of the program counter will be taken out to the address pins, and then the data corresponding to that address will be moved to the processor. Okay. So, and once the data is taken, then automatically this will be incremented. So, that is the program, the work job of the program counter. Then you have the stack pointer. So, stack pointer for storing some data, some important data away from the main data and main program. So, we can locate, we can allocate some memory area as a stack. Okay. And we can initialize that memory location, and that is called as the stack pointer. We will study all those things in detail when you study about the various instruction sets and programming of the microprocessor, and then these are called as the flag register. So, depending on the, so once some arithmetic and logic operation takes place, you may get a negative result 0, and then auxiliary carry, and then what is called as parity carry. So, these bits will be set. Okay. So, again the meaning of all this we will see in the coming slides. Okay. So, in summary, so the microprocessor consists of a control unit, arithmetic logic unit, registers, and then external signals, okay, which are called as the interrupt signals, and then it also contains the internal data bus. Okay. So, the processor performs arithmetic and logic operations on 8-bit data. So, we saw about the register A. So, the register A is called as the accumulator. Okay. So, this accumulator is part of the arithmetic logic unit. Okay. So, this accumulator or the register A can be accessed by the programmer. Okay. So, this accumulator or this arithmetic logic unit contains a temporary register also. Of course, any operation that is being done, some temporary results will be stored in the temporary register. The arithmetic logic unit will store the temporary registers temporarily in this register, but we will not be able to access this temporary register through instructions. Then we have, so we saw that we have the general purpose registers. Again we will see the architecture. So, the architecture, it is basically accumulator, flag register, B, C, D, E. So, general purpose register, all these are 8-bit registers, and then this is the these are the 16-bit register. Okay. So, B, C, D, E, H, L are 8-bit registers. So, they can be used as 8-bit registers, or they can be combined together. So, H and L can be combined, and D and E can be combined, and you can use it as a 16-bit register. Okay. Then apart from holding data, so this HL register, they can be combined and they can hold address also. Okay. This HL register, not only they can hold data, but they can hold address also. It can hold as a pointer. Okay. Now, let us see the accumulator. Okay. So, accumulator, of course, it is a special purpose register. Okay. So, B, C, D, E, H, L, they are all general purpose registers. This accumulator is a special purpose register. Okay. So, again it stores, just like any general purpose register, it can store the data, but at the same time the logic and then the arithmetic operations can be performed only in the accumulator. Okay. That is why it is a special purpose register. Okay. And then after performing the arithmetic logic operation, the result, of course, it stores the result and it can transfer the result to memory or to any other input output device. Okay. So, it stores performs the logic arithmetic operation, stores the result, and transfers the result to a memory or input output device. Now, the another special purpose register is the flag register. So, flag register is a 8-bit register. Okay. So, when the microprocessor performs a logic or arithmetic operation, okay, so the contents of the accumulator may become 0, may overflow. So, these conditions are indicated by this individual flip flops. So, the flag register consists of individual flip. So, the register means a single bit, single flip flop. Okay. So, 8 such flip flops put together makes a register, full 8-bit register. Okay. So, these are all operated individually. Okay. So, they are given the names as you see here, S, Z. X means it is not used, then again X not used, and P, C, Y. Okay. What is the meaning of that? S means sign flag, Z 0, AC means auxiliary carry flag, P means parity flag, and CY means carry flag. Okay. So, what is the meaning of this sign flag, carry flag, and all these things we see? Okay. So, first sign flag, okay, this is S. Okay. So, this will indicate the sign of the data. So, in binary arithmetic, the most so can be used to represent the sign. Okay. In arithmetic operation, so in arithmetic we use positive numbers and negative numbers. So, in normal we use plus and minus sign, but digital computer cannot understand plus minus. Okay. So, you have to give some binary notation for that plus and minus. So, the binary notation, the last, so in signed arithmetic form, the most significant bit represents the sign bit. Okay. So, if the most significant bit is 1, it is a negative number, if it is 0, it is a positive number. Okay. So, if you are using the signed arithmetic form, then in that case, so whenever the most significant bit becomes 1, you have to indicate that it is a negative number. So, this will, after the arithmetic operation or logic operation, if the most significant becomes 1, then this flag will be set, it will become 1, otherwise it will become 0. So, that 1 means, so if it is set 1, it indicates that it is a negative number. Then again when you add 0 flag, okay, so we will see the 0 flag. So, 0 flag, so when you add 2 numbers, you may get a 0 as the result. For example, let us see, we are having 2 binary numbers, you see here. So, after add operation, so you have written the instructions to add, you have stored this in 2 registers, and then say in one accumulator this another register, and you give the instructions to add. So, you add these 2 numbers, okay. So, you add these 2, you get the result as 0. Of course, you get a overflow, but the result is 0. So, immediately this 0 flag will be set, okay. So, the 0 flag will be set. Okay. So, this is the function of the 0 flag. Then another is carry flag, okay. So, when you add 2 numbers, you may get a overflow. Okay. If you subtract, you may get a borrow, you may have to borrow the number. Okay. So, you see here, you are adding these 2 numbers, these 2 binary numbers. So, you add, so you get a carry. In this case, you subtract. So, this number is smaller, okay, this number is smaller, this number is larger. So, when you subtract from a smaller number a larger number, you get a borrow. Okay. So, in such case, the carry flag will be set. So, the carry flag is set here, as you see here. Okay. Then you have the other flag, auxiliary carry, and then parity. So, the auxiliary carry will be set when there is a whenever there is a carry bit from the. So, if there is a carry bit from here to here, okay, when you add this number, suppose there is a carry from here, this point to this bit to this bit, okay. So, from D3, so D0, D1, D2, D3, from D3 to D4, if there is a carry bit, this auxiliary carry will be set. So, this auxiliary carry will be set, okay. Then there is what is called as the parity flag. So, parity means count number of ones. So, any binary number you take, okay, counting the number of ones, 1, 2, 3, 4, 5. So, this has got 5 ones, okay, 1, 2, 3, 4, 5. So, 5 number of ones. So, 5 is a odd number, and here you see 1, 2, 3, 4. 4 is a even number. So, this binary bit has got odd number of ones, and this has got even number of ones, okay. So, this information is sometimes used for error correction, okay. So, hence depending upon whether the number of ones in the result. So, after performing the arithmetic or logic operation, the result contains how many number of ones, even number of ones or odd number of ones. So, accordingly this will be set, or it will be set to 1 or set to 0, okay. So, if the parity is even, it will be made 1. So, if the parity is odd, it will be made 0. So, this is the use of the parity flag. Then let us see program counter. So, we have seen about the functioning of all these bits, all these accumulator we have seen, flags, and then general purpose registers. Now, we have the program counter, okay. So, this program counter is the one that is responsible for sequential execution of the instructions. So, the instructions in the microprocessors or microprocessor is stored sequentially. Sequentially means one after the other. So, starts from location 0, then 1, 2, 3, 4, like that, it is sequentially stored, okay. So, you have to start from the memory location, and then say start from say 0 means you next 1, 2, 3, 4 in a sequential order, you have to keep on accessing the memory location. So, this program counter holds the address, and once it takes data from that address, then immediately it will point to the next address, that is, it will sequentially go from say location 1, 0 means it will go to location 1, 2, 3, 4 in a sequential manner. Okay. So, it always holds the address of the next instruction. So, once it takes the instruction from a location 5, then next it will point to location 6 and take the instruction from 6. Of course, in between, of course, later on we will see we can change the flow of the program also by using the jump instruction, that is anytime we can change the content of the program counter, and we can make it to jump from that particular instruction to any memory location, okay. So, obviously, since it has to hold 16 bits, okay, the address is 16 bits. So, it has to be 16-bit register. Okay. So, now let us see the overall summary of briefly we saw about the functioning of various pins of the microprocessor. Of course, we have to see them in detail in the coming units. Okay. Now, then we saw about architecture of the 8085. Okay. So, the programming model of the 8085, the various registers, what are the functions of the various registers, general purpose register, special purpose register, and then the 16-bit registers, that is the program counter and the stack pointer. So, all these things we saw. Okay. So, in the coming class we will see about more about working of the processor, the stack pointer and other functioning of the other register. So, for your understanding, kindly try to find the answer to the following questions. So, question number 1, what are the general purpose registers and then the special purpose registers in the 8085? What is the function of the sign flag? Mention when the auxiliary carry flag will be set. What is the use of the parity flag? So, we have come to the conclusion of this episode. So, in the next episode, we will see more about the architecture and then the programming techniques. Thank you very much.